Number 11. Brent is making a wooden display case for his baseball collection. He has 24 balls from the American League games and 30 balls from the National League games. He wants to display the same number of baseballs in each row and does not want to put American League baseballs in the same row as National League baseballs. How many rows will Brent need in the display case to put the greatest number of baseballs possible in each row? So I've got 30 of the National League balls, 24 of the American League balls, and I want to put the greatest amount of balls in each row. So what they're asking you to do is find the greatest common factor between 24 and 36. So what is the greatest common factor, or between 24 and 30? Well, I know it can't be more than 24. 24 doesn't go into 30. Then the next biggest number that goes into 24 would be 12. 12 won't go into 30. Then 8 goes into 24, but 8 won't go into 30. 6 goes into 24. 6 will go into 30. So I know my GCF is equal to 6. Now, if you couldn't come up with that, you can do a factor tree. 4 times 6, 2 times 2, 2 times 3. 30 is 5 times 6. 5 is prime, and 6 is 2 times 3. So then you ask yourself, well, what do these numbers have in common? They have that 2 in common. They have a 3 in common. So 2 times 3 is how you get the 6. So that means I can put 6 balls in every row. So I can take 6 of the National League balls, put them in a row. So if I put 6 in every row, how many rows am I going to need for that? Well, I've got 30 of those balls, so if I do 30 divided by 6, that means I'm going to need 5 rows to do it. So now my picture just proved that it really did take 5 rows to put 6 balls in each row. Well, then now what about the American League balls? Well, to do the American League balls, there were 24 of those. I want to put 6 in each row, so it's going to take me 4 rows to do that. So now my picture proves that I needed 4 rows to get those 6. The question wants to know how many rows will Brent need in the display case to put the greatest number of baseballs possible in each row. So they want the total number of rows. So now you have to add up your 5 plus your 4 and say 9 rows. So in a sentence, Brent will need 9 rows. And you can count the rows just to make sure that it really was 9 rows. When you see the directions, factor each polynomial. What does that mean to you? Factor means you have to write a multiplication problem. So if I'm going to factor by the GCF, which is the first question you ask yourself on any factoring problem, is there something I can divide out? So the greatest common factor between 2 and 4, the lowest number is 2, so the biggest my GCF can be is 2, and 2 does go into 4, so my GCF is 2. Between the letters, there's 3 D's, there's 1 D, so they have a D in common. So then you factor that out. So basically what you're doing is you're dividing each of these by 2D. Or you can say 2D times what gives me 2D cubed? Well, I'm missing a D squared. 2D times what gives me 4D? Well, I'm missing a 2. 2D times 2 is 4D. So you can either think of it in terms of division or you can think of it in terms of what's missing when I try to multiply it back. So 13 between 1m squared and 8m to the 5th, between 1 and 8 is a 1, but I have m's in common. This one has 2m's, that one has 5m's, so the most amount of m's in common is 2 of them. So basically what you're doing is you're dividing by m squared. So m squared divided by m squared is 1. Or if you think of it as missing multiplication, m squared times what gives me m squared? You got to multiply by 1. Then m squared times what gives me negative 8m to the 5th? Well, it's going to be negative 8. I've got 2 m's, but I need 5, so I'm missing 3. Number 14. The greatest common factor between 12, 4, and 8. Well, the biggest it could be, it'd be 4, because that's your littlest number. 4 does go into 12, 4 does go into 8. So 4 works. They all have an x in common. You've got 4 x's, 3 x's, and 2 x's. So the most amount of x's they have in common is 2, so that's x squared. And then basically what I'm doing is I'm dividing each one of these terms by 4x squared. Or if you think of it in terms of missing multiplication, 4 times what gives me 12? That's 3. X squared times what gives me x to the 4th? X squared. 4 times what gives me negative 4? Well, 4 times negative 1 gives me negative 4. X squared times what gives me x cubed? Well, I'm missing an x. 4 times what gives me negative 8? Negative 2. X squared times what gives me x squared? Well, that'd be 1, and 2 times 1 is still just 2. Now, just to make sure I'm factored completely, my parentheses don't have a common factor, but that's a trinomial with my highest exponent being a 2. So that's in the form ax squared plus bx plus c. So you actually have to check to see, can I factor that trinomial? Well, my favorite method of factoring was the Korean method. So 3, I can do 3 times 1. To get negative 2, I can do negative 2 and a positive 1. So if I multiply going down, that's 3. If I multiply going up, that's negative 2. If I add those together, I get positive 1, not negative 1. But if I switched these signs, then this would be a positive 2. This would be a negative 3, and that does give me a negative 1. So this can actually be factored one more time. So if I put my x's in here, that trinomial factors into 3x plus 2 and 1x minus 1. But you can't forget your GCF in the very beginning that you took out, so there's still a 4x squared out here on the front. So that actually could be factored one more time. Now I have a multiplication problem. All my addition and subtraction signs are in parentheses, and I've completely factored it. Okay, for number 15, it's another trinomial, so I think, oh, well, I can start off doing, it's ax squared plus bx plus c, so I can do Korean method. But the first question you always ask yourself is GCF. And 3, 6, and 3 have a greatest common factor of 3, so I can actually divide out that 3. They don't have all the same variables, so I can't do anything with the variables. But if I divide each of these by 3, I'm going to end up with k squared. 6 divided by 3 is 2, so I have 2k. And negative 3 divided by 3 is negative 1. So now I look at this and I think, oh, I've got x squared plus bx plus c. Maybe that can be factored again. So you kind of have to check, is the Korean method going to work on this? So 1k squared will be 1 times 1. And the only way I can get negative 1 is a negative 1 and a positive 1. So if I do 1 times 1, I get positive 1. 1 times negative 1, I get negative 1. That would add up to 0. So this one, that trinomial cannot be factored anymore. So this truly was my final answer.